Good day, folks. This is tutorial number 19, and it's in a playlist called Dynamics Scenario in 3D Experience. Now, I will be introducing the concept of position motor excitation. In the previous tutorial number 18, I introduced velocity motor excitation, which really refers to the case where it's a continuous motion of the motor. In the case of position motor excitation, uh, the motion of the motor is not continuous. Maybe you have a rotary index table which requires this table to move at specific angles during specific time, so that an operation is done on it. So this kind of a tutorial and this kind of a position motor excitation is gearing is geared toward the application that I have in mind there. Stepping motor, for example. Now you need to be in dynamic scenario because this is available only if you're in dynamic scenario stage, and that's where we have the icon position motor excitation. I already had tutorials on law excitation, segmented excitation, and sketched law excitation, but now motor, uh, position motor excitation. Excuse me, I still haven't recovered from a cold. Now, because we are in dynamic scenario, you have to define the mass or the weight of the objects that are involved. And when you click on the position motor excitation, the top dialog box opens up and it says pick your command basically. Now, if your command is prismatic, then it's basically defining the motion, the motion of the prismatic joint based on the graph that you see here. So this once you select that prismatic joint, you get this option. You can change the length, the distance traveled. You can change the initial time here, 5 seconds, for example, 10 seconds, etc. Okay. Now, if you use the pull down menu, you can also do the oscillating one. And when you do the oscillating, you have to specify the amplitude, frequency, etc. Now, if you pick a revolute joint, you get the same kind of thing that you need to do, but it's revolute, and it's just that certain things are in terms of angle. For example, in that many seconds, how many angles, etc. And there's a pull down menu for oscillation. Now, the example that I'm going to do for you is mostly on the prismatic joint. However, I will do the revolute joint also very quickly, but I don't go through it as details as I have in the prismatic case. And the example, incidentally, that I'm going to do is going to be something like that. So we have a track, we have a block on it, which is centered here for visual purposes. And I'm going to use, when I create this prismatic joint, I will use the offset being the end plate here, end face here, and the end face of the track, and use that as what I have in mind. And here's the documentation or help documentation on 3D experience. So let's go ahead and do that. I'm going to insert the track first, insert 3D part. I'll do the track. Okay, so let me right click properties, call it track. Track. Okay, let's go make it. So double click. All right. So on that vertical plane, I will sketch my units are in millimeters here, so I'm going to make a nice centered uh, rectangle. Oh, actually, yeah, that's fine. Sure, 2 millimeters by 10 millimeters. So let me see for a second. So this is going to be, let me do the other one first. 2. Okay. And then I do this one 10. That's going to be the cross section on my track. I'm going to pad it symmetrically by 100 millimeters in each direction. Okay, so this is going to be my track. And then I'm going to insert the block, right click, insert block or 3D part. I'm going to call it block. And here's the block. Okay, let's go make it. Double click to make it here. And on this vertical plane, I will sketch a centered box, rectangle, and dimension this thing to be 10 millimeters. Okay, and the height, I mean, that's really not important, but I'll make it also 10. All right, exit, and then pad it in both directions by 10 millimeters, which means a total of 20, total length of 20 millimeters. Okay, so there's my block. So all the way to the top. All right, we can make the joints right now. First of all, this track is fixed, so engineering connection fix the track. Okay, that's done. And then I'm going to have a prismatic joint. What is that? Prismatic joint. And the template that I'm going to be using is right here. Line and line, plane and plane. Okay, so this line and this line, this plane and that plane. And for the offset, because I'm going to be controlling this, remember, when you use position control, position motor control, which we are doing in this tutorial, or velocity motor control, you need to have commands on them. Okay, so you need to do this last piece, control. Okay, so I'm going to use the end face of this block and the end face of the track. So right now it says 90 because this is 90. Remember, this whole thing was 100, half of it, and this was 10, so that's 90. We said fine. We don't want to do any contact calculation. Okay, good. So we're pretty much done here. So now we're going to go to uh, mechanical systems design. Because we're going to be doing a dynamic scenario, first of all, we have to introduce weights or masses. There's only 2 parts here, so I clicked on that, wait for this to pop up. 100% of it is missing, so I select the track. That's totally irrelevant, but you have to put the mass on it. So I check this box so that it puts properties of steel, but it's not going to be used. And then select the block. Again, click on the hyperlink, check this box over there, put the properties of steel on it, and then close it, and then close it. So we have mass so that later I won't complain. Now, let's create our mechanism representation. And if you look at it, what is this? You have a prismatic one, and of course a fixed joint, fixed part. Now this arrow, uh, I'm not very happy with the way this is set up. On one of my computers, it works fine. The other one is not. But if it goes in the wrong direction, I'm going to flip this arrow. You can do that by selecting it. See that? You can flip it. But just leave it the way it is right now. Okay. So we have done this. And now we go, then now we're going to go to uh, mechanical systems experience. We already created the mechanism. We don't have to do those check boxes. All right, so here is where the uh, position motor excitation is. You click on it, and this dialog box that I'm showing you is actually the one that was in the slide, which was right here. This is the one, or that one, same thing. But now I have only a prismatic joint here, so I go and select it, the command from it. You need this command. If you don't have this command, then you won't be able to pick it because this is asking for the command, not for prismatic joint. You select on it, and it says, what do you want to put as the information? So let me try the following. First of all, I'm going to make 1 second here, 1 second, okay? And then this distance, this time, also 1 second, okay? And the the distance that is supposed to travel, that remember that end is supposed to travel, I'm going to make that thing 90. So if I do a 10-second interval, uh, you will actually get to that endpoint. So we say fine. Let's see, we made everything here. Uh, this is 1 second, this is 1 second, and then this is going to be reaching 90 millimeters. So we say fine. Now notice that you can do distance, you can do oscillation. I'm going to do distance right now. Good, good. So now if you, let's create a probe here, position probe, and I'm going to monitor, for example, that corner point. Okay, let's create a dynamic scenario. Position motor we created, probe we created. Total duration of the simulation is 10. If I do a 10, this is going to go over it, but let me make this thing a 9 so that you can see it better. 9 seconds. All right, so it looks like we're in business, and we're going to run it, except that it may be going in the wrong direction, but we'll see. It's supposed to go to the right. That's what I wanted. 1 second, and then starts moving after 1 second. Ah, see, this just does not make sense. We have to, this arrow does not look right. I'm going to flip it. No problem. Flip it, and now run it. So it's going to go to the right now. All right. So let's go and check it out. How do we check this out? Well, let's plot something. Plot. Okay. Uncheck everything. Deselect everything. If you check the first box, this is not on the probe. It says this command that this position motor excitation, show me how it was done. And yeah, how it was done. And now show me the position of that vertex point, and they better match. Almost, yeah, almost. And you see, of course, they match, except that one of them is going to give you distance. The other one is going to give you essentially a position. So if you look at the red one is the excitation that you inputted. So it's 0 until 1 second. Then in 1 second it rises, and then it has to close the gap to go to 0. Now this blue one is the position of the vertex. So it started at -10. If you look at that vertex point that I took, is actually at location -10, and then it goes to -100. So this is the same information. It confirms the fact that it is doing what it's supposed to. It is correct. And now, of course, if you want, you can go and plot the velocity and all that stuff. So let me go ahead here. For example, let's say show me the velocity in the x direction, linear velocity, and when you look at this, plot, you might say, oh, why does it look like that? So let's see what actually we did here. Let me close this for a second. Let me close this. Go back to my excitation. Let's see what we did in excitation. We said that the first 1 second sit put, the next 1 second go to position 90 millimeters, 90 millimeter, go to the end. And this should be in 1 second, and then sit there for the remaining of the simulation. So it is zero here, zero velocity here, zero velocity there, and a non-zero velocity over here. First it kind of accelerates and then it decelerates, okay? So in fact, if you go here, that's why the plot looks like this. If you go back to the results, if you go back to the results, let's do it again. Deselect all. Show me the velocity, x linear velocity. See, the first 1 second, it was sitting put. The next 1 second, it accelerates and then decelerates because it reaches the 90 millimeter position and it sits there, pretty much like that. So it looks like that. If you plot the acceleration, it should be a positive acceleration here and negative acceleration there and 0, 0, obviously. So if you go and do the linear x-linear acceleration, let me not do this. Yeah, you can see that. Accelerating, 0, and then uh, accelerating, and then decelerating, okay? And that's what you got. That's what it looks like. Now, if you go and change this, for example, if you go to your position motor, and make this thing, for example, over let's make it a very smooth motion. So over maybe 8 seconds, 7 seconds. All right, let's go run it and see what happens. Accelerating and then decelerating and then sits at that location until the end of the simulation. Okay, so let's plot it. Same story. Let's go ahead and plot the velocity, for example. Velocity, x linear velocity right there and there. Okay, so that takes care of this. Now suppose we do the following. We go here, and instead of this uh, distance, we do oscillating. It says what frequency. So let's leave it like this and see what happens. And then the amplitude oscillation is going to be 100 millimeters, so it's going to go back and forth. No phase here, so that's okay. Run it. And then it's going to go back. Yeah. Okay. Just to make it look better, so let me let me do the following. Let me go here. We have two things we can do. We can increase the frequency, or we can increase the time. Let me go and increase the frequency. So I go here and make it maybe 1 hertz. Oops. Let me try it again. 1. I'll put down 1. Okay. And now simulate. It's going to take a lot more oscillation. You can see that. Yeah, and that 100 that I put as the amplitude is actually the amplitude oscillation. So that's what it is. Okay, so that takes care of this. All right, so let me do quickly a problem involving a Revolut join. So let me start with another assembly file. Pretty simple. Insert the base. Insert same story. So insert 3D part. Call it the base. This is just a cylinder. So I'm going to make it. I'm going to ignore any dimensions because we know where we're going with this. Exit and then add it. That's fine. And uh, how about the cylinder or the thing that's going to be turning basically? So let me go ahead and insert a 3D part, and this is going to be rotating mass. Rotating mass. Copy, paste. Okay, let's go make it. So on that top plane, I'll use sketch. I'll make another circle, and maybe with a little bit of a small circle here, so that I get an indicator when I pat it when it's rotating. Let me flip that. So later on, when it rotates, I know that it's rotating because there's a hole here. Now, yeah, that's pretty much it. You go all the way to the top. Let's do our joints now. Fix the base. Okay, did I do that? Fix the base. Okay, and then create a revolute. I'll do the fourth one. This axis and the axis of the base, and this plane and the plane of yeah, the plane of this base. And for the angle, I'm going to control, for example, the angle between a vertical plane of this and a vertical plane of that. So for example, YZ and YZ, I need a command because right now they're sitting on top of each other, which is fine. I don't want to do any contact connection. So you go all the way to the top, go to mechanical systems design. Let's apply masses. So let's do the base. Uh, what did I cancel that for a second? Okay, let's try it again. Okay, let me do the base. Click on the hyperlink. Click on the checkbox here. It puts properties of steel on it. That's fine. And then do the rotating mass. Click on the hyperlink. Check this box. It puts the properties of steel on it. So, okay. And now create a mechanism. Let's see what it is. It's a revolute joint. It's angle driven. You can see that. You need to have a command, otherwise you can't put that position motor excitation. Okay, so we're done here. Now we're going to go to mechanical systems experience. All right, so first we do the uh, yeah, we have everything. We don't need anything else. Go and do the right here position motor excitation. And this is the second box. This box is that dialog box. It's the same thing that you saw before. So you can select the control being this command one, and now you put down whatever you think is right. So let's see now. Let's actually make it the same thing with work with distance. Here, distance is going to be, of course, angle. You can see that. See that? Angle right there. So I'm going to do an oscillation. Oscillating. Let's make it 1 hertz and make it as the amplitude, maybe 45 degrees. Okay, and run it. Or have to create dynamic scenario, put the excitation in it, say okay, and then run it. See that? It's almost 10 times. That's pretty much it. It's almost exactly the same as what you did in the prismatic case, but yeah, it's rotation. All right, folks, good luck.